How Newton might interpret gravity was adequate to permit us to fly from the Earth to the Moon. However, it sort of got to make you giggle and make you think you would be able to complete the journey to the Moon and back. That is, it eventually utilizes something, I guess. Everything in our universe seems wonderful. There are regulations governing the whole universe. However, certain secrets have remained bizarre in spite of numerous years of examination. For what reason? What is the nature of time travel? The nature of reality? For what reason does gravity exist? For what reason does time pass more quickly when we travel at the speed of light? These are inquiries that have held our attention for centuries. Think about the possibility that I will allow you to be aware that gravity is manifestly false. It is merely a human brain creation. This may appear unbelievable, but that is exactly what the well-known physicist needed. Let's dive, as recently stated by Brian Cox, into the idea of gravity and the reason why time slows down to find out what in the world is gravity. The issue we really have, we need to transcend Newton to solve the problem, not so much in what he got right, but in what he completely failed to address. There's an issue with Newton's theory of gravity, which is that it merely allows us to anticipate how things will move under its influence. It is silent about the nature of gravity or even how it works. It just permits you to calculate things. Newton knew this, of course. He basically just said that it's down to God. In fact, he said that the most wonderful arrangement of the sun, the planets, and the comets could continue under the jurisdiction and direction of an intelligent being. In other words, he gave us the instruments to determine how the objects move around, yet he said, "Don't ask me how or why, that's down to God." In the enormous universe that includes us, there are secrets waiting to be uncovered. Among these secrets are the remarkable characteristics associated with time and gravity, two important aspects of our existence. Imagine an existence where time acts peculiarly, where it can slow down or speed up, and where the force that serves as our foundation may not be what it appears. This is the jurisdiction of Albert Einstein's theories of relativity, where our comprehension of time and gravity takes a strange turn. Albert Einstein, a name known to many, gave us a new viewpoint on the universe with his theories of relativity. His contributions laid the foundation for how we might understand how time behaves under different situations, particularly when we travel at outrageous speeds. Everything started midway through the 20th century when Einstein proposed two pivotal theories, the special theory of relativity and the general theory of relativity. In 1905, the special theory of relativity was published. It changed how we understand time and space. In simple terms, it tells us that the laws of physics remain the same for all observers who do not accelerate, regardless of their course of action. This theory introduces the concept of the effects of relativity, including the widely accepted notion that time can stretch or slow down under certain situations. Among the most captivating thought experiments used to explain how the light clock's time dilation works, imagine being inside a spaceship moving at an incredible speed, close to the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors that are perpendicular to the direction of movement. To an observer inside the spaceship, the light appears to proceed straight up and down, but to an outside observer who's not moving with the spaceship, things look different. They see the spaceship moving at high speed and notice the light beam has to reach the mirrors by traveling a greater distance. According to the laws of physics, the speed of light is the same for all observers, so it must appear that the light beam travels a longer, slanted path. Now, here's where it becomes interesting. Whenever the time it takes for the light to travel, its path ought to be identical for both observers, the individual inside the spacecraft and the other outside. However, because the route is longer for the outside observer, it appears to take more time for the light to complete its travel. At this apparent moment, there is a difference in the two observers' time, what Einstein referred to as time dilation. Time slows down for the observer moving relative to the observer who is at rest, so time behaves in a different way here. It's not just dependent on your movement. Experiments have confirmed these examples of relativistic effects, including particle accelerators like the Large Hadron Collider, where particles can reach speeds close to the speed of light. Scientists have to account for time dilation to make accurate predictions and demonstrate the unique theory of relativity. It opens up a world where time is not a constant but can be stretched and compressed depending on your motion. It challenges our everyday intuition and leads us to the conclusion that the universe operates in ways that go well beyond usual experience. Einstein's special theory of relativity, presented in 1905, changed our perception of the universe's fabric, especially in terms of the theory of time and motion. In its essence, it demonstrates that the physical laws apply consistently for all observers who do not accelerate, regardless of their movement. To comprehend the special theory of relativity better, we need to dissect one of its core concepts. According to the special theory of relativity, the speed of light is the same for everyone, no matter their motion. Whether you're standing stationary or moving at high speed, light always seems to travel at the same regular speed, around 299,792,458 meters per second. This idea conflicts with our usual encounters, where typical speeds add up when we're moving. It's as if the universe has an inherent speed limit, and that speed is the speed of light. In special relativity, as we understand it, there may not be simultaneous events for everyone. If two events happen at different locations and you're moving relative to those events, what you see as occurring at the same time may not occur simultaneously for another person at a different vantage point. This seemingly odd idea challenges our conventional notion of time. The concept of time dilation might be one of the most captivating and tangible implications of the theory. As mentioned earlier, time can speed up or slow down based on how you move. The faster you move, the more slowly time passes for you in comparison to a stationary observer. This effect becomes more pronounced when you get close to the speed of light. Imagine two identical twins, one on Earth and another being launched into space at a significant fraction of the speed of light. When the twin who travels through space returns, they will be younger than their Earthbound sibling. This phenomenon, often known as the twin paradox, is a real effect of the passage of time. This unusual behavior is caused by the consistency of light's speed. As the space-traveling twin accelerates to high speeds, their clock appears normal to them. However, to an observer on Earth, the space-traveling twin's clock appears to slow down because the twin is moving compared to Earth. Another result of special relativity is length contraction. When an object moves quickly, its length in the motion-related direction appears shorter to a stationary observer. At typical speeds, this effect is minimal, but it stands out more as an object approaches the speed of light. One of the most well-known physics equations, E equals mc, is an immediate consequence of special relativity. According to this equation, mass and energy can be combined. It means that mass can be converted into energy and vice versa. This principle is essential for comprehending the behavior of particles at high speeds and the energy produced in processes like nuclear reactions. Special relativity's effects go beyond a theoretical concept. It has real-world applications. For example, GPS systems rely on the precise timing of signals from satellites. However, because these satellites are moving relative to us, the effects of time dilation are present. If not accounted for, these effects would cause significant errors in GPS accuracy. The effects of special relativity were not included in the GPS report. Computations used by our navigation systems would be significantly less accurate. The special theory of relativity requires us to reconsider our intuitive notions of time and space. It demonstrates that the universe operates in ways that differ from our typical experience. Time is a concept, but it is not absolute. It is relative to movement, the constancy of the speed of light, and the relationship between energy and mass. These are underlying concepts that have been confirmed by numerous experiments. Now, let's delve into the general theory of relativity, another groundbreaking idea put forward by Albert Einstein in 1915. This theory brings us into the realm of gravity, demonstrating a significant connection between gravity and the very fabric of the universe. At its core, the general theory of relativity challenges the notion of gravity as a force that acts at a distance between masses. Instead, it demonstrates that gravity results from the curvature of spacetime. This idea is more straightforward than it may sound. To understand general relativity, we need to consider the universe as an entity with 4 dimensions that combines 3 dimensions of space with a single dimension of time. In this 4-dimensional spacetime, massive objects like stars, planets, and even you cause spacetime to curve around them. This curvature is what we perceive as gravity. Consider spacetime to be a vast, adaptable fabric. A massive object like Earth makes this fabric wrinkle. When you place a smaller object, like a ball, near Earth, it rolls toward this notch. This is similar to what happens when an object falls under the influence of gravity. Gravity is not a mysterious force, but simply the result of objects following the curvature of spacetime. General relativity provides a robust explanation for the motion of celestial bodies in our solar system. It accurately predicts the orbits of planets, such as the elliptical path followed by Earth around the Sun. The old idea of gravity as an attractive force didn't fully account for these orbital motions, but the concept of curved spacetime does. One of the most notable confirmations of general relativity came during the solar eclipse of 1919, when Sir Arthur Eddington led an expedition to observe the bending of starlight by the sun's gravity. According to the theory, the sun's massive presence would curve the path of light from distant stars, causing them to appear slightly displaced from their usual positions. Eddington's observations matched Einstein's predictions, providing strong evidence for the curvature of spacetime. Another fascinating prediction from general relativity is the existence of black holes. These are regions of spacetime where gravity is so strong that nothing, not even light, can escape. Black holes arise naturally from the equations of general relativity when a massive star collapses, creating a singularity of infinite density surrounded by an event horizon beyond which there is no return. In recent years, we've gained direct evidence of black holes through gravitational wave observations, ripples in spacetime's fabric caused by the acceleration of massive objects. When the black holes merge, they generate gravitational waves that travel through the entire universe. The detection of these waves by observatories like LIGO Laser Interferometer Gravitational Wave Observatory has confirmed the existence of black holes and provided further support for general relativity. One of the more perplexing features of general relativity is the concept of time dilation near massive objects. Just as time slows down when moving at high speeds, it also slows down in strong gravitational fields. This means that time passes more slowly for an observer near a massive object compared to someone farther away. This effect, known as gravitational time dilation, has been observed and measured. For example, precise atomic clocks set at various elevations indicate that time moves slightly faster at higher altitudes, where the gravitational force is weaker. The implications of general relativity extend beyond extreme cosmic events. They are crucial in understanding the large-scale structure of the universe. The expansion of the universe, first observed by Edwin Hubble, is explained by the general theory of relativity. The theory describes how the fabric of spacetime itself is capable of stretching, carrying galaxies along with it. The general theory of relativity has transformed our perception of the universe and gravity, revealing that gravity is not a mysterious force acting from afar, but a result of the curvature of spacetime caused by massive objects. This elegant idea has been confirmed by various observations and studies, from the bending of light to the detection of gravitational waves. The concept of gravitational time dilation further emphasizes the interplay of time and space. Einstein's theories of gravity have transformed our view of the universe, providing an in-depth understanding of the nature of reality. While they may not offer all the answers, they have opened new avenues of exploration and inquiry. Einstein's theories challenge us to rethink the fundamental nature of time, space, and the universe itself. They suggest that our intuitive comprehension of reality may be constrained and that the universe operates in ways we cannot fully grasp through everyday experience. Theories like relativity remind us that scientific knowledge is a quest for understanding, where each new finding leads to new questions and deeper comprehension. In conclusion, Newton's theory of gravity laid the groundwork for understanding celestial mechanics, but it was Einstein's theories of relativity that changed our understanding of gravity as a fundamental feature of spacetime. The special theory of relativity introduced the concept of time dilation and the unchanging speed of light, challenging our perceptions of time and simultaneity. The general theory of relativity further advanced our understanding by describing gravity as the curvature of spacetime caused by mass and energy. This idea not only explained gravitational phenomena like the orbits of planets and the bending of light, but also predicted intriguing phenomena such as black holes and gravitational waves that have since been observed. Einstein's theories continue to inspire and guide scientists in their endeavor to comprehend the universe on both its largest and smallest scales. They have altered our view of the cosmos, revealing a universe where space and time are intertwined and where the force of gravity is the geometry of spacetime. As we continue to explore and test Einstein's theories, we are reminded that the universe is full of mysteries waiting to be unraveled. Each new discovery brings us closer to understanding our place within it.